Now, yes. Okay, so welcome everyone for the IPhT Colloquium. Today we are very happy to have Jesse Taylor, who will be talking about QCD theory meets information theory. So Jesse is a professor at MIT and also in the Institute for Artificial Intelligence and Fundamental Interactions. And he's in Paris for a year in IHES and IPhT. So if you want to talk to him, don't hesitate. He will be around for a while. And with that, take it away.
Great. Well, thank you very much. Really a pleasure to be here in the Paris area. And as Anton mentioned, I'm on sabbatical and a linear combination of IHES and IPhT. So here's a picture of me in front of IHES. This is the staircase that I take every once in a while. And then if someone could take a better picture of me than this brick wall to represent my visit here at IPhT, that would be fantastic. But I arrived here in August. I'm trying to make sure that I'm here whenever I'm in town on Tuesdays, but if you want to interact with me, please send me a message. And in particular, an emerging theme for my sabbatical, which will also be featured in this talk today, is a kind of two-way street between theoretical physics and machine learning optimization. And these are ultra preliminary plots. These are just happen to be the plots that were on my laptop when putting these slides together. On the left-hand side, this is a kind of machine learning way of thinking about the modular bootstrap equations. And the fact that all these curves have a loss of order 1 means that I can think in a statistical way about sampling from the distribution of operators in a CFT, which is fascinating. And I get something that has like a chi-squared-like statistics, which is maybe not the way that people usually think about conformal field theories in the modular bootstrap. And then in the reverse direction, thinking about machine learning optimization in the language of theoretical physics, this red curve here is some standard machine learning optimization. And then the green curve here is what happens if you follow a geodesic in function space, and you find that the loss rockets down to 0. And I'm super excited about work that I'm doing in that direction, using physics insights plus a knowledge of kind of computational structures to try to advance the way that we optimize machine learning problems. So if you have a theoretical physics problem that you think that could be reframed as optimization, let's chat. I've been talking to many people, both about the application of this style of algorithm and then also about theoretical physics problems that may or may not have an optimization framing. And what I'm going to be doing in this talk is telling you how certain aspects of QCD theory do have a framing in terms of optimization. And you'll see exactly what that is. And I'm going to try to keep this at a relatively light level. We'll see if I succeed or not. But happy to have conversations for the rest of my year in Paris about this and other topics. So the starting point for this talk is actually going back to my postdoc days. So I dug up some slides from 2008 when I was working on exactly the same problem as I'm going to be presenting today, only I was thinking about it as QCD theory through the language of QCD theory. So when I was a postdoc with Frank Tachman and Christian Bauer, worked on this framework for generating synthetic collisions at the LHC using a tool that we call Geneva, generating events analytically. And the buzzwords from the QCD community is that you're trying to do parton-shower matrix element merging or matching. So the parton shower is a way of capturing all orders information in QCD through iterative recursive splittings. And matrix elements are first principles QCD calculations based on Feynman diagrams. And you wanted to merge this kind of all orders information and this fixed orders information into one coherent whole. And so your goal is to try to estimate backgrounds for the LHC, standard model backgrounds to beyond the standard model signals. You had these kind of two strategies. This was the more fixed order strategy. This was the more resummed plus non-perturbative physics modeling strategy. And aspirationally, in 2008, I and many other people were thinking about ways of merging those things together. And there's actually been enormous progress in this area, and none of it involves me. And the reason why none of it involves me is because when I started my faculty position at MIT, I applied for my first grant from the US Department of Energy. And a US DOE reviewer in 2011 dissuaded me from pursuing this research direction. And so I did not work on parton-shower matrix element matching. I worked on other aspects of QCD, in particular jets and jet substructure. But still in the back of my mind, I've been frustrated that I got derailed from this exciting developments in this area. And now we're going to revisit that topic, but now through a different lens. So for this talk, you don't need to know anything about parton-shower matrix element matching, because we're going to talk about it in this more abstract language of information theory. And then my job basically is to convince people who are QCD experts that this is actually a useful strategy for thinking about how to approach this problem. And as I said, there's many people who have made essential contributions to this way of thinking. Here we're going to give you a complementary perspective on how you might accomplish the same task. So let me just tell you the punchline of this talk. So the punchline is that we're going to do a theory synthesis, synthesize multiple different theoretical calculations through what I'll be calling centaur science. I'll explain what that is. So centaur is, of course, the mythical Greek creature that's part human and part beast. And you're going to see, let's say the human part is a QCD part and the beast part is machine learning. We're going to see how those things can fit together. And so instead of treating this technical subject of parton-shower matrix element matching as a domain-specific problem in QCD, we're going to treat it as just a generic problem in information theory. So again, you don't really need to know anything about the QCD underpinnings. But remarkably, this is going to reveal a new understanding about the difference between fixed-order calculations and resum calculations as captured by ordinary versus logarithmic moments. So in the last part of my talk, I'll try to explain this. And this will be surprising to the people who work in QCD theory, because I'm going to show you a calculation that you're not supposed to be able to do, but we'll just have to do it because the machine told us to. And then once you realize that you have to do it, you do it, and the structure turns out to be interesting. And then there's not probably very many experimentalists in this audience, but this approach could dramatically simplify the kind of experiment theory interface for precision predictions. And you can ask me about that offline if you're interested. And this work is in collaboration with Ben Assi, Kyle Lee, and Stefan Höcke. And I've been dragging them, these are folks who are more firmly in the QCD community, dragging them into the world of machine learning. But at the end of the day, if you look at our paper in PRL, you see plots like this. And this looks like a standard theory plot. You have experimental data in black. You have various error bands corresponding to different accuracies. So it looks like a theory calculation that you're familiar with, maybe. But the underpinnings turn out to have this more information theoretic framing. And that's what I want to tell you about today. So what we're going to do is we're going to first kind of advertise this philosophy of centaur science. And I'll advocate that when physicists think a little bit like a machine, that we can translate our thorny theoretical challenges into optimization problems and let the machine solve them. Then I'm going to tell you a little bit about the basics of machine learning and information theory and leveraging the flexibility of loss functions to learn and constrain physically meaningful moments of distributions. And then telling you about this QCD aspect that logarithmic moments, which to my knowledge has never appeared in the QCD literature before, they are particularly powerful probes that distinguish different calculational strategies. And even if you aren't an expert, hopefully you'll see that the structure of these logarithmic moments are different than what you might have seen or expected to see from perturbation theory. OK, so to launch in, I should say that part of me being on sabbatical right now is me escaping my responsibilities as director of a US National Science Foundation-funded venture, the Institute for Artificial Intelligence and Fundamental Interactions, known as IPhi. We started 5 years ago. We are undergoing our renewal process right now. So regardless of whether we are renewed, which we might find out even as soon as next week, or not renewed, there will be some French alcoholic beverage that I will be consuming. We'll see just which brand of alcoholic beverage it is, depending if it's more celebratory or more miserable. This is a joint venture between MIT, Harvard, Northeastern, and Tufts universities. And the goal of this institute is to kind of bring together people working on deep learning, that is artificial intelligence, and then deep thinking, that is physics principles, and then gaining a deeper understanding both of the way that the universe works, but also on the way that artificial intelligence works, that is, how does machine intelligence behave. And one of the things that I'm most proud about our institute over the past 5 years is the way that we've educated this new generation of AI plus physics talent. We have this spectacular group of IPhi postdoctoral fellows. We have a robust summer school and workshop series. So this is a photo from the 2024 edition where my two students, former student Rikab Gambhir and current student Sean Benevetti, they're very smiling because they're at this intersection of physics and AI. And through this institute and through my own research, realizing that there really is this two-way street between machine learning strategies and my own field of particle physics. So in the context of high energy physics, it seems important to teach machines to think like a physicist, to meet the standards of scientific rigor and performance that we expect. And I could give you a whole nother talk about how you can embed, for example, symmetry principles into neural networks or bake in certain uncertainty guarantees into neural networks. And that's teaching the machines to do what we already do as physicists. So that would be a fun talk to give. But then there's this other direction, which is maybe more uncomfortable, which is that to fully capitalize on AI technologies, we also need to teach physicists to think like a machine. And again, this makes me feel a little bit uncomfortable because now I have to learn a new language. But as you'll hopefully see, this kind of more abstract framing turns out to be relevant for a variety of types of problems. And this kind of two-way street between physics and machine learning, I've been calling this centaur science. And centaur science is not something new. Progress in computation and information theory has long been intertwined with progress in the physical sciences. And as you'll see in this talk, statistical mechanics has a viewpoint from, of course, condensed matter systems, but also from a viewpoint from information theory. And this intertwining is something that we are seeing even more and more in the age of AI. And when I started talking about this concept of centaur science, Kyle Kramer, who's a faculty member at University of Wisconsin-Madison, he sent me this fantastic cartoon from the New Yorker magazine that I think highlights the challenge for those of us who are working in this space. So this is from earlier this year. So the centaur scale. What we're trying to do is find the optimal mixture between machine learning and physics knowledge. We're trying to figure out the right amount of horse, if you'd like. And in this talk, you're going to see an embodiment of this cartoon. You're going to see what it means to have kind of QCD type framings, which is accurate but kind of ugly. And then this is way too slick machine learning. And then the right amount of horse is the right merging between kind of a physics and an AI mindset. This merging of physics and AI was also highlighted by the 2024 Nobel Prize in Physics, which celebrated, in some sense, this dialogue between physics and computational strategies. And you're going to see in a couple slides that Boltzmann machines, which were Hinton's work. Of course, Hinton himself is more of a computer scientist than a physicist, but this idea of Boltzmann machines is going to inspire some of the things that I'm going to be saying about today. But the idea that learning can happen through dynamical systems, that statistical reasoning is a good way of approaching science, and that scientific discovery can be advanced by these AI strategies, this is something that I'm quite passionate about and something that I'm exploring for my sabbatical. So while I'm on sabbatical, I'm not actually playing the role of IPhi director, and I have an interim IPhi director, Mike Williams, who is an LHCb experimentalist. But he's been doing some very cool work at the interface of these two fields. So since I'm off in Paris, I feel like I should show at least one result from Mike's work. And this is showing this dialogue between physics and AI. So there's this fascinating phenomena that's been known in machine learning that's known as grokking. So grokking is a phenomena where machines trying to learn something, doesn't learn. And then someone leaves the computer on overnight. And then suddenly it has an epiphany, and it suddenly kind of snaps into focus, and it figures out how to solve a problem. And what Mike and collaborators showed is that this behavior really is kind of like a phase transition in some kind of either supercooled or superheated, I guess a supercooled system. And so here we're going to see the internal workings of a AI algorithm that's trying to do modular arithmetic. So it's trying to learn the rules of modular arithmetic. It's not learning, and learning. And then you're going to see the information kind of crystallize in this movie. So you start off with it can't figure out the structure of modular arithmetic. The internal latent space of the machine learning is kind of chaotic. And then boom, it snaps into focus. And you get this beautiful clock-like structure that represents, of course, the structure of modular arithmetic. And again, Mike and collaborators showed that this behavior is very similar to the phase transition that you would see in a physical system. Then realizing that the machine could learn these type of structures, then you can ask, well, are there any other data sets out there that might be more interesting than modular arithmetic? And indeed, Mike, who's trained as a nuclear physicist, wants to find out about nuclear physics. So he takes the nuclear physics data tables, asks the machine to try to come up with an internal representation of the nuclear physics data tables, And instead of having a circle like this, what he finds is he finds this helical structure. And in fact, one of his recent papers is called the DNA of nuclear physics, because it actually turns out to be kind of more like a double helical structure. And you realize that just by looking at the data in nuclear physics, you find that the machine has figured out about things like magic numbers and other structures that nuclear physicists have known about, but the machine finds it kind of spontaneously, if you like, through the data. And then also it gets better predictions than specialized nuclear models. And so this dialogue between AI and physics is quite robust, and Mike's research here is an example of that, using physics insights to understand how an AI system works, and then once you realize how it works, using that to learn something else about a physical system. Okay. So for this talk, I feel like a good starting point for what I'm going to be saying is to start from a point of skepticism. Okay, so some of you maybe are already on board with the idea of using machine learning for scientific applications. Some of you might be worrying about the machine hallucinating, and then how could it possibly give trustable answers. And there's this simultaneously inspiring and infuriating paper that is raising some of the dangers of thinking like a machine. So this is from Soledad Villar and David Hogg. And their position paper is machine learning good or bad for the natural sciences? To which the answer is yes. But let me just read from their abstract to highlight the tension that they are showing here. So here's the abstract. Machine learning methods are having a huge impact across all of the sciences. However, machine learning has a strong ontology in which only the data exist, and a strong epistemology in which a model is considered good if it performs well on held-out training data. These philosophies are in strong conflict with both standard practices and key philosophies in the natural sciences. Okay, so maybe you haven't thought about the philosophy of science recently. Let me try to translate this into a simpler language. So this is my cartoon version of the argument of this paper. What they're saying is that if you're a machine learning person, what exists is the data. And success means that you've accurately modeled that data. So when we use AI, for example, to generate synthetic deepfake images, the data that we're using is data from the wild of pictures, and accurately modeling of the types of pictures that could be generated from taking a camera picture of something, that would be defined as success. And so data is the thing that exists, and success corresponds to accurately modeling of that data. In the natural sciences, though, there is plenty of stuff that exists that's not data. For example, quarks and gluons and Feynman diagrams and coupling constants. We have things that don't appear in the data itself, but nevertheless we think has a reality to them. Quantum fields don't exist in the data, and yet quantum fields, we think that is a way, if not the way, to understand the microscopic universe. So we believe in latent structures, that is, hidden structures that are underpinning the data. And success is understanding those internal structures, understanding the rules that govern the microscopic and macroscopic worlds. And what Hogg and Villar are saying is that these things are in tension with each other. So let me just highlight this tension in the example that I'm going to be showing you in this talk. Yeah?
Why are they in tension? Because if I take, a neural network, it has some internal representation of the data. So I can always think about internal representation of the neural network as much as internal representation in my brain of some data. So why is there a tension?
So the tension, so the question was, why is there a tension here? Because of course I can think about the internals of a neural network as being a type of understanding. And there are plenty of examples in machine learning where you get fantastic, accurate modeling of the data with no interpretable latent space. In fact, there's certain ones that it's kind of provable that you don't actually generate, you don't learn features, that you don't extract underlying structures. But the whole point of this talk is that they're not actually in tension, but you have to be careful about how you do it. So this paper is in some sense a must-read. I think they are both very, very right and very, very wrong. I think they're very, very right to highlight this tension. And indeed, a lot of my conversations with computer scientists have been frustrating in part because the definition of success has been different. But fundamentally, I don't think that they're actually in tension. We just need to know what we're doing. So in particular for the problem today, where we're going to try to mimic data from the Large Hadron Collider, and so that mimicry of data from the Large Hadron Collider, that'd be called a generative model. So what if you could generate synthetic LHC collisions that were completely indistinguishable from real LHC data? So the experiment does their collisions, you just hit return, 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 and let's say they're completely indistinguishable. Would that be considered success or not? And according to Haag and Villard, this conflicts with the epistemology of the natural sciences. That is, just because you can have mimicry doesn't mean that you can actually understand the underlying structures. So for example, you could mimic the Higgs boson discovery in the sense of you could mimic the diphoton mass spectrum perfectly, but would you really know that there was the appropriate pole in your scattering diagram corresponding to Higgs boson resonance? So this, I think, is what people are scared. And people have even thought about, train a neural network on the LHC data, store the neural network, and throw out the raw LHC data. And I think that makes people uncomfortable, and understandably uncomfortable. Just because you have mimicry doesn't mean you have understanding. On the flip side, what if you could generate synthetic LHC collisions based entirely on first principles QFT calculations? Yeah. By indistinguishable, I mean that by a statistical measure of similarity, of which we can decide which one we want to use, that measure of statistical similarity is one such that, let's say I take 3 inverse Atabarns of data from the CMS, and I say how different is that from 3 inverse Atabarns of data from the Atlas experiment, and then I take 3 inverse Atabarns of synthetic data, that these are all roughly the same distance apart by some measure of statistical similarity. Well, I'll give you an example of a measure of statistical similarity that we use here.
This ignores the fact that, for example, you're looking at tails of distribution. You're looking essentially at very, very small part, and there's huge numbers of observations you can do on these.
Yeah. So the.
I mean, it's an abstract concept, sure. They're indistinguishable, right? As a practical, computable thing.
Yeah.
This measure of indistinguishability is not something you can compute in any short amount of time.
So. Right. So there's a very interesting question about how one goes about assessing indistinguishability. Machine learning itself gives you relatively efficient ways of quantifying the similarity or dissimilarity between data sets. And people actually here at IPhT have worked on various strategies to try to quantify the similarity between synthetic data and real data and put a number on it. And one way of thinking about putting that number on it is like thinking about the p-value, like saying, given data that I've observed, can I say with some probability that the data that I observe this is distinguished from the underlying model with some fidelity? The what?
The weighting of the bulk and the weighting of the tail.
That's right, and this is actually something that you get to decide as a user about how you want to address. So you get to decide what your measure of similarity is, and there's different measures of similarity that allow you to weight, for example, bulk versus tails of distributions. And the easiest way of doing this is in terms of like statistical concepts, but this is actually a choice that you get to make as a user. And part of the arguments that are happening in the people who are in this top category is actually what is the measure of similarity that you should use. But I don't see this as a problem. I see this as a research opportunity. And if you look at the stats literature, there are reams and reams of different strategies that are used for similarity. In my own research, optimal transport theory has been a really useful measure of similarity. And that's one that I can defend from a first principles perspective as well. And so I find that to be a useful notion of similarity, which I'm happy to talk to you about. But this is kind of separate. The point here is like here, if you're able to do this, let's say we even agreed on the notion of similarity, I think we would say that we haven't learned anything. Whereas if we could do synthetic LHC collisions based entirely on first principles QFT calculations, then we would say that we would understand something in the sense that you could compare data to your QFT calculations and then extract coupling constants or the masses of fields, or even try to tell the difference between standard model versus BSM physics. But whereas the top is at least in principle doable with our current infrastructures, the bottom here is not doable. We have various non-perturbative models. We can only compute things to certain accuracies in quantum field theory. And so this is where this tension shows up. There's the thing that you can do from the machine learning perspective, but we usually would not assign that as having as a being a way of understanding the underlying theory. But then in terms of the underlying theory itself, we don't have the ability at the moment to take a given theory and generate synthetic collisions. And this is the tension that is reflected in what Haag and Villar are saying. And the point of this talk here is that they're not in tension, they're just an opportunity for synthesis. And this perspective of centaur science is that we're going to combine models of LHC data for the full phase space. These are going to be imperfect. We're going to acknowledge their imperfection. And then we're going to combine them with first principles predictions whenever they're available. And this is this literal synthesis of kind of a machine learning strategy versus a first principles calculational strategy. So if you want to take an extreme version of this, imagine a bunch of hallucinating AI chatbots that give you a model of the LHC data that you don't trust at all. Okay, but we're going to tame that. So actually, what is a group of hallucinating AI chatbots? Like, what's the collective noun in English for a group of hallucinating AI chatbots? So I've been calling it a hallucination of chatbots as the collective noun. So you have a hallucination of chatbots, and then, but you can then constrain them using first principles predictions. And it's not at all obvious that this should be doable, but information theory is going to give us a strategy for accomplishing that. Okay, so let me give you 2 slides just to give you kind of the sense of where we're going, and then I'll dive into each of these things in turn. So the first thing is we're going to get inspired by strategies in the machine learning literature for building generative models. We're getting inspired by Boltzmann machines, which of course was the topic of the 2024 Nobel Prize. So a Boltzmann machine is a generative model, that is, you can generate synthetic data, that samples according to a statistical distribution, and in this case, that statistical distribution is coming from an Ising model. So you say you have some collection of spins, and you're going to learn an energy, that is, learn the weights and biases, or couplings and biases, such that if you were to sample according to Boltzmann statistics, you would generate synthetic samples that would mimic whatever data that you have, and you encode that in terms of an energy. So we're going to take an inspiration from this idea of encoding information about a system in terms of its energy. So just to remind you, this Boltzmann factor itself, where does e to the minus e over t come from? This comes from maximizing entropy subject to a constraint on the average energy. And I'll go through this derivation in detail in a couple of slides. But this e to the minus e over t, it's not something that's just a randomly chosen factor. It's something that you can appeal to entropy principles to say why you think that something should be distributed in this way if you know something about its average energy. And we're going to take this idea and we're going to now lift it to a collider physics context. So collider physics data is not a bunch of spins. It's more dynamic than that. It corresponds to continuous variables over actually many, many dimensions. And so what we're going to do is we're going to lift this idea of maximum entropy to maximum relative entropy, that is relative to a prior. So going from spins to continuous phase space and entropy to relative entropy, the equivalent of the Boltzmann distribution is saying that you start off with the thing that you're doing things relative to, so that's known as the prior. And then this e to the minus beta e is going to get generalized to e to the minus a bunch of terms where we have a Lagrange multiplier that is the thing that's imposing the constraint, so that's like the 1 over kt, and then some constrained quantity. And so what we're going to do, almost literally, is take this is now like a centaur, this is the prior, one end of the beast, which is, you can imagine as a hallucination. In our case, we're going to take it as being a parton shower event generator, and then we're going to constrain it using first principles calculations, and this is the structure that we're going to achieve. Okay? And I'll explain where this comes from. Now, if you're thinking about this from, well, what insights do I gain from QCD about this? Let's say I convince you that this form is useful. What do I learn about QCD? Do QCD calculations actually take this form? Do QCD calculations look like something times exponential of something? And the answer is yes. So again, I'll say more about this at the last part of the talk. But if I just pluck a random QCD calculation from my own work, and we say, does it look like something times exponential of something else? This is the structure of a next to leading logarithmic calculation, where the something is this prefactor, and then the exponential of something else, this whole exponential structure is called a Sudakov form factor. And actually, these exponentials are ubiquitous when you're thinking about parton shower matrix element matching as before. And this will actually be the type of structure that will emerge from the calculation that we'll be doing. So to a QCD theorist, this is some next to leading logarithmic calculation. A machine learning practitioner might look at this formula and say, ooh, I could do neurosymbolic learning and try to learn things like gamma functions and other structures of the calculation here. But if you're the Centaur scientist and you're being inspired by Boltzmann machines and generative modeling, there's a fascinating parallel here that we're going to exploit. We're going to exploit the fact that to a Centaur scientist, this Sudakov form factor is going to be kind of like a Boltzmann factor. The Lagrange multiplier, the 1 over kt, will be played by the role in QCD of what's known as the cusp anomalous dimension, roughly speaking. And then this is going to enforce a constraint. Well, a constraint on what? So we have to look inside of that exponential. What is actually in that exponential? Exponential depends on r. R is called a radiator. This first part is basically like the cusp anomalous dimension, roughly. This L, ignore the B for a second. The L gets squared. The L is a logarithm. So it's the second logarithmic moment. Just like Boltzmann's mechanics tells you that you constrain the energy, e to the minus beta e means you constrain the average energy of the system. Here, the fact that it's e to the minus something times log squared is telling us that we want to constrain the second logarithmic moment. And to my knowledge, logarithmic moments have never been measured or calculated before in QCD. But this is the natural thing to do if you just look at the structure of these calculations. It's the natural thing to constrain in this more Centaur scientist approach. And so I'll explain that by the end of this talk. Yes?
So in the previous slide, typically you have that this probability distribution is on a space that is high dimensional.
Yeah.
If I take, I don't know, a statistical system.
Yeah.
In that case, the next slide,
Yeah.
do you have some high dimensional?
Absolutely. This thing is the full phase space. This is where every single pion goes, everything. So this X is hiding a lot of things. So this is the full phase space of every possible thing that can happen at the LHC. And so that's the hard thing to do. But then for the precision calculation, that's a 1D distribution. So how do I do that? But again, it's the same thing about having a spin system and then the average energy. A spin system is high dimensional, but the average energy is one quantity. So we have the same thing here. We have the high dimensional space, but then it's being projected down by these constrained quantities to a small number of things that I, as a pencil and paper theorist, could imagine calculating. So we really are going to be making predictions for the whole phase space, but the constraints are going to be low dimensional. High dimensional phase space, low dimensional constraints. Yeah.
Your physical constraints, you use the Lagrange multiplier.
I'm using the Lagrange multiplier method of optimization,
Yes.
but the constraint that I'm using is going to be on a theory calculation, yes.
And the constraint you put inside this beta.
Yes. So the Lagrange multiplier is beta, and then whatever is constrained is this quantity. This is just Boltzmann mechanics, by the way. Oh, yeah.
Yes. But inside this, I told to students of data science, and we used the more general form of HGB,
I don't know what you're referring to.
Hamilton-Jacobi-Bellman method.
Okay.
And it is more general, and it is very appropriate to physical situations.
Uh-huh.
Like, you say, not only quantum chromodynamics, but it would be my question is your idea to put the optimization as for the learning.
Yeah.
Is very optimistic, just I said, I should say, and it would be used for other theories, physical theories, I mean, not only. Yes, but did you try to put Markov chains inside the learning and represent inside the Markov chains the physical situations and optimize?
Right.
Is there some
So let me see if I can translate what you're saying. So the question was, here I'm using a very simple model, right? And the question is, could I do something more intricate? And in particular, you said, could I use Markov chains as a way of representing this? So the Markov chain picture, roughly speaking, is actually how a parton shower works. And that is a well-known, accurate way of modeling. but it doesn't allow you to correct things by certain precision calculations. And this is the best that we came up with thus far, but it's also only the first thing that we tried. And so if one thinks about taking a system, some statistical model, and imposing prior knowledge on it in some way, I think that's just a general framework. And the thing that I'm advocating for is that normally you would say, if you've done a calculation of a constrained quantity, then all you should do is look at that constrained quantity. It would be like looking at a thermodynamic system and saying, all I want to study is the energy. I don't want to study the microstates. In this framing, though, there's nothing that stops you from also looking at the microphysics as well as the macrophysics as you like. And for data analysis at colliders, our experimental friends really want to have the full phase space. As theorists, we can only capture and calculate restricted quantities. And the balancing of those two is achieved by this formula. But there may be other formulas that could also achieve that type of balance and would be equally successful. There's nothing specific about this other than saying this is something that achieves my desired criteria, as I'll sketch out in a couple of slides. OK, so that's where we're going that I need to justify to you. And just to say, this kind of centaur science approach is continuing this tradition of relating properties of physical systems to concepts in computation and information theory. OK, so now let me go through the derivation just to remind you how this works and just show you some sense how simple what we're doing is really saying, and just tell you about some of the basics of machine learning and information theory. So for the work that I spend a lot of time doing is studying the properties of jets, which are collimated sprays of particles that are produced at the LHC, and coming up with different ways of quantifying and measuring the properties of these jets. From a machine learning perspective, what I'm really trying to do is I'm trying to solve an optimization problem to tackle a particular aspect of jet analyses. And just as one example, not the only example, but as one example of something that you might want to do, is you might want to know, given a jet, what was its origin? Jets come from the fragmentation of high-energy quarks and gluons. So a very kind of simple thing you could do is to say, what's the probability that this particular jet is a quark jet versus this particular jet is a gluon jet? And learning that relative probability of quarkness versus gluonness, that is a very standard thing that happens in machine learning. And let me just show you the derivation about how you do machine learning optimization, just to show you how straightforward this is from both a physics and a machine learning perspective. So this is kind of a machine learning 101. So let's say I have two distributions, P and Q, but all I have is samples from it. It could be samples from experimental data or samples from a Monte Carlo event generator. So I have samples P and samples Q. My goal is to estimate this ratio because the likelihood ratio between two possibilities, that is the optimal way of telling whether possibility P versus Q is actually realized. So if I see a given jet, I see a given X, a property, and then I say, is it more likely to come from P or Q? To do that, I need that ratio. And the way that a machine learning person would set up this problem is they'd say, OK, let's build a loss function. That loss function will depend on samples from P and samples from Q. I take F, which are some neural network, the details don't matter, and I try to optimize log of F averaged over the P sample and F minus 1 averaged over the Q sample. And if you look in the stats literature, they'll tell you that the optimal answer that you get if you had an infinitely flexible neural network and infinite amount of training data is indeed that the loss is minimized at the ratio P over Q, and moreover, that the value of the loss at that minimum is a statistical quantity, the Kullback-Leibler divergence, which could be used, for example, as a measure of statistical similarity if you wanted to. So you did not come to the general seminar today to get a stats lesson. You came to hear about physics. To a physicist, all I'm doing here is Lagrangian mechanics. In fact, the most simple version of Lagrangian mechanics, that you can really think about this L as if it were an action. And if I don't use this angle bracket notation, but turn it into something that's more familiar, then this really is just Lagrangian mechanics. So I have an action. OK, it doesn't depend on t. It depends on x, which is high dimensional. And my Lagrangian here, in the asymptotic limit, if I had infinite training data, is just related to the probability p of x, the probability q of x, and then that log of f and f minus 1. And then you could just do Euler-Lagrange right now. You could just, in your brain, like take the derivative of this with respect to f, set it equal to 0, and you can quickly convince yourself that the solution is p over q. So of course, we don't have infinite training data, so there's deviations from this result because I only have finite training data. And a lot of the magic of machine learning is coming from exactly dealing with that non-asymptotic statistics. But asymptotically, this is what you would get. And so this requires a shift in focus from solving problems to just specifying the problems and then doing essentially numerical Euler-Lagrange. And in fact, you could even do like more complicated things for optimization. And people actually talk about like Hamiltonian learning, where you have both positions and momentum, some fun stuff like that. But for the purposes of this talk, we just want to say, can I specify an optimization problem that corresponds to the problem of interest, and then let the machine find an answer? OK, so what are we trying to do? We're trying to do Parton-Shower matrix element combinations. That is, Parton-Shower is a general purpose event generator that can make arbitrary LHC predictions, but at relatively low accuracy. We want to combine it with matrix elements. These are specialized QCD calculations that can make high accuracy LHC predictions for specific observables. And we want to find something that through optimization achieves a general purpose event generator for the LHC that will provably reproduce any specialized QCD calculation. That's the goal of this optimization. So I need to now specify a loss function for which this would give me the solution. So as already advertised, the way we're going to do this is through information theory and information theoretic optimization. So we're going to predict a distribution by maximizing entropy. And if I had a discrete data, then a standard way of talking about maximizing entropy is through the Shannon entropy, where the Shannon entropy is related to summing over all configurations of probability of that configuration times log of 1 over the probability. And you can show that maximizing this, that is maximizing the p that would maximize the entropy, is saying that the p's would be 1 over n. Now, this is a very standard thing that we do in statistics and entropy, where we say that each configuration would get equal weights. But I want to emphasize that this was a choice. You chose that equal weights was somehow special. You were making a decision when doing that. And while doing this as a decision makes sense when you have discrete data sets, when you have continuous data sets, the Shannon entropy is not defined. And you need to lift yourself to relative entropy. But relative entropy comes with a choice. And now the choice is like really in your face. So this 1 over n here, which I've highlighted in orange to highlight that this is a choice that you made. If I'm doing maximum relative entropy, which is just the KL divergence that we saw before, the maximum relative entropy now depends on Q, which is the prior choice of what you thought kind of you're measuring your entropy relative to. And that's something that you have to decide. We're going to use a Parton-Shower to decide that. So that's going to be our general purpose event generator. And then I want to learn that P, well, if I do optimization with P unconstrained, then the thing blows up in my face. Instead, I want to make sure that that P actually is normalized so that it's a proper probability distribution. I introduce a Lagrange multiplier to do that normalization. And then the extremum of this relative entropy, properly normalized, extremizing over P, is e to the minus beta naught times Q, and beta naught equals 0 when you solve the Lagrange multiplier. And that tells you that P equals Q. So this is just the standard story that maximizing unconstrained entropy, this is just equivalent to choosing a prior. For the discrete case, we choose that equal probability is the thing that we think of as being the baseline. In the case of relative entropy, then the thing you're relative to, which I'm calling here a prior, that's the thing that you anchor yourself to when you optimize over optimize over entropy. OK, so this is our Parton-Shower or our hallucinating chatbots. This is the thing that is our baseline that we now want to improve. So how do you improve it? You now do constrained optimization. You put in these constraints. And our choice of how we're going to constrain things is by constraining moments. So we have more Lagrange multipliers. C is going to correspond to someone's theory calculation. For what? For some observable, which is defined by F. And an observable is just an integral over phase space of that value, so like an expectation value or a moment. And now the theorist gets to decide, hey, what do I want to compute? How hard do I want to work to compute this integral? The simplest thing I could do is compute just the total cross-section, which just gives me probability 1. Or I can compute something more intricate, like an energy if I'm doing thermodynamics, or a particular collider observable. I get to choose what that is, and then I anchor it down to that value. And then the solution here is what was advertised before. So this is just Boltzmann mechanics. So the same manipulations as Boltzmann's approach to StatMech, where the Lagrange multipliers set the values that satisfy the constraints. Now note that this formula here is written in terms of the Lagrange multipliers beta. The theorist provides the actual value of the moment c. And this is where machine learning or machine learning software comes in play, that I have to solve the Lagrange multiplier to make sure that these moment constraints are satisfied. And that's a bit of an annoying optimization problem. But of course, machine learning people have generalized toolboxes for solving annoying optimization problems, and so you just use that. So then to take this extremum, we now want to solve it. And how do we do it? We say, well, let me guess some values of beta. I have a target value. I have a current moment value for that assumed choice of beta. I want to make the moment, the current value of the moment and the target value of the moment the same. So I put a loss function that says I want their difference to go to 0. And then I just release machine learning software at this problem, optimize my loss function until it goes to 0, numerically minimize the loss to estimate these Lagrange multipliers. And as long as these moment constraints aren't strictly incompatible, this works for any set of basis functions. So I could have a resummed calculation, this is enough for the experts, a resummed calculation of the peak distribution of thrust, and then a fixed order calculation for the tail part of thrust. I can actually have different bin widths or overlapping bins, like they all can be satisfied in this framework. You just tell me what you've computed to what accuracy. I throw it into this constraint. And then the only choice you have to make is if you want to be a little bit more clever with the denominator and maybe try to do something that actually accounts for, let's say, your uncertainties in your calculation to make this look more like a chi-squared if you wanted to. Okay? But that's the framework. That's it. We use Lagrangian mechanics to impose constraints, numerically using machine learning, and that's what we're going to be doing. Very, very simple, but also very, very different way of thinking about how you do parton-shower matrix element matching. I never have to touch the internal workings of my parton shower. I just impose the constraints that I have confidence in. I'm going to skip the next slide. The next slide is if you're someone who likes more fancy schmancy machine learning. There's a way of doing the same thing using adversarial networks. Let me not talk about that. There's many numerical strategies to solve the optimization problem that I showed you before. The one I showed you is just the simplest and the most directly connected to Boltzmann mechanics. OK, so machine learning, it provides a bridge between well-established statistical methodologies, things like relative entropy, KL divergence, and such, and sample data in particle physics and beyond. And that's the thing we're taking advantage of, that you have this ability to, even if you don't have analytic distributions, sampled information is enough in order to combine things together. Yeah, question?
Do you have to sample from when you learn the parameters?
Yeah, so in general, I have to sample here.
This can be hard, no?
This can be very hard, and that's why you collaborate with Monte Carlo experts who know.
But it can be hard, not just because it's high-dimensional, but because it has like local minima and this. I mean, you need to find like activated paths and so on.
Absolutely, and you run into the same challenges that people who build, as I said in this slide, adversarial networks have, mode collapse and all that. I'm not saying that this is easy. I'm saying that this is a general framework that that one could apply if one wants to be able to do this synthesis. And then, of course, the implementation becomes a fascinating one. And one of the things that we're running into right now is exactly what you're saying, getting stuck in local minimum and whatnot. But now you've translated it from being a kind of a theory question about whether you can in principle do it to now a more practical question of optimization strategies. And I find that kind of wonderful, because now I could just offload my problem onto a computer scientist who can help me figure out numerical strategies for doing this efficiently. Yeah. OK. So I told you the method. Now you can ask the question, did I learn anything about QCD from doing this? Like, great, I achieved parton-shower matrix element matching. I've achieved the thing that I wanted to do for my postdoc days. Have I actually learned anything? And just in the interest of time, let me just skip these slides about how actually computation often helps us learn things. But let me just skip that. And just come back to this slide here, where I said that there's this kind of analogy between a QCD calculation and this particular kind of Boltzmann structure. And let me unpack this a little bit more. Okay. So there's an apocryphal quote about lies, damn lies, in statistics. So let's talk about this from a statistics perspective. So I'm telling you that our framework is based on computing constrained moments, average values, means, variances, and such. And this is a general mathematical question, which is the problem of moments, which is that given a probability distribution, and you compute its moments, first, second, third, and so on, and given an infinite set of them, can you reconstruct the underlying distribution? And so you might be thinking that that's what I'm doing here. I'm saying I have a distribution that I'm trying to understand theoretically, and I'm going to use moments as a way to kind of build up that distribution. And what I want to say is that actually this is not a good idea typically in particle physics contexts. An example where you just fall flat on your face is for the standard Cauchy distribution. So the Cauchy distribution that appears when you have a resonance, this is famously a distribution that has no mean or higher moments. That is the procedure that you would do in the method of moments. These moments are unconstrained. Of course, there's strategies of analytic continuation to make them well-defined. So it's obvious in some sense the average value of x should be x0, but if you actually follow the procedures mathematically for defining the moments of this distribution, they don't work. And so this is somehow telling you that standard moments are not always the right solution to your problem. And if you think about other types of summaries that you might make of your distribution, that could actually be better at capturing the underlying dynamics. So instead of saying, I want to compute moments, really what I want to know is, given a probability distribution, what summary statistics best capture the key physical properties? So here we have the cosmic microwave background, and you can ask, what properties of the CMB do we think actually capture its properties? And we know, because the universe is homogeneous and isotropic, or we expect it so, that we think that a power spectrum is the right way of capturing this distribution. But more generally, I don't know a generic way of answering this question of, given data, what are the summary statistics that I can use to capture the key physical parts about that data? To my knowledge, this requires just domain expertise to figure out what the right thing to do is. And so the story that I'm telling you here about using moment constraints, this is an opening for us to use our theoretical understanding to say, well, which moments do I want to use? As I said here, the general problem of moments is not well defined. And yet, moments are, or summary statistics are, a good way of capturing probability distributions. So for each domain, you can ask, what are the summary statistics that are best for the problem at hand? So in the case of QCD, one summary statistic that is used often is something that's called thrust. Thrust measures how much radiation in a collider event is aligned along an axis. The details of this don't matter. And then if you want to summarize the summary, so thrust itself is already summarizing many, many particles into one number. And then I want to summarize the summary by taking the average value of that. And my colleague at MIT, Ian Stewart and collaborators, they have been doing these heroic calculations of the thrust distribution at increasing accuracy. So this is a next to next to next to next to next to next to leading logarithmic calculation for the in the strong coupling constant, where what they're computing is the mean value of thrust. So that's a first moment, the mean value of thrust. And they would say that the mean value of thrust is a good way of characterizing the theoretical thrust calculation. Their theoretical thrust calculation is best summarized by taking its mean. But that may be different than experimentally. Experimentally, I mentioned that you have these Sudakov form factors, these Sudakov peaks. If I look at the experimental distributions for thrust, the mean value does not align with a peak typically. It's offset. And so if I am given an experimental thrust distribution, actually, to best characterize that, I would like to say, well, where's the peak location? Where is the dominant probability density at? And you could think about that as like the difference between a mean versus a median. Like these are different summaries that we can use. And there may be a tension between the thing that I can calculate theoretically and the thing that would actually experimentally describe my data. And that's the thing that I want to explore right now. So to do this, as I mentioned already, that we're going to talk about logarithmic moments. So I want to show you doing a logarithmic moment calculation, what it looks like. So you'll just have to trust me that this calculation here is a particular limit of QCD, and this is the probability distribution as a function of the strong coupling constant. It depends on the strong coupling constant. It depends on color factors. And this tau here is this thrust summary. So I have probability distribution of that thrust summary. And then this exponential factor, this is my Sudakov form factor. This has all orders information in the strong coupling constant. And famously, the Sudakov form factor has log squared of thrust in it. And now I want to look at this theory calculation and ask, how would I summarize it? What are different strategies for summarizing it? And do they look the same or different? So ordinary moments, the thing that Ian Stewart and friends are computing, ordinary moments have a nice series expansion to alpha s. The lowest order in alpha s is just alpha s. And this is something where I can march order by order in perturbation theory, make my Feynman diagrams increasingly complex. This is ordinary moments. What I'm telling you from the Centaur science analogy is that we want to look at logarithmic moments, which I said have never been computed before. Okay, let's compute it. So using this simplified calculation, we'll just compute the logarithmic moments. And this thing looks very weird to someone who's used to seeing fixed order QCD calculations. In particular, I see alpha s's in the denominator, which is weird. In fact, I'm supposed to take a square root. This is very strange. This is something that I did back in 2015, so 10 years ago. This is called Sudakov-safe observables. These are observables which do not have a fixed order expansion in alpha s. But because of the Sudakov form factor, you regulate divergences, but you get these kind of funny non-analytic behaviors. And so just taking the lowest versions of this. So the mean, this is what the theorists have calculated previously, this is directly proportional to the strong coupling constant. And this characterizes very well fixed order information. But now I'm telling you that actually to characterize the distribution, you should also be looking at logarithmic moments. And particularly the logarithmic mean tells you the location of the Sudakov peak. And look at this funny calculation. This is very weird to a QCD person. You have a 1 over the square root of alpha s. And 1 over square root of a coupling isn't supposed to happen in a fixed order expansion. And indeed, it doesn't come from a fixed order expansion. It comes from this resummed Sudakov form factor. And this is a way of characterizing resummed information. And so actually these two different ways of characterizing the distribution, they have a different interpretation in terms of the type of QCD calculation you should do. Yes?
I have a question.
Yeah.
What's the argument of alpha s in those two expressions?
Oh, like alpha s evaluated at which scale?
What's the scale?
Yeah, so this is a ultra simplified leading log at fixed coupling calculation, so there's no scale here. Now, if you want to go to higher, if you want to go to like calculate these things and say what scale is contributing there, this becomes a very interesting question. And in fact, I don't know how to express it simply in this form. The work that I did with Andrew Larkowski and Simona Marzani on these Sudakov-safe observables, the scale setting, if I remember right, we set the scale inside of an integral and then did a numerical integral. And so saying that there was one value of alpha s is not what we ended up doing. But it's an interesting question what the appropriate scale choice is here. But here, this simplified calculation, I'm just doing it fixed coupling to demonstrate the strange non-analytic structure.
Well, since you're going to use those expressions, I just put it because by now you know that none of this formula makes sense.
Oh, absolutely not. Yeah. So I'm not using this expression. I'm going to showcase you. And then the calculation we're going to do is on the next slide.
No, but just to finish with
Yeah.
that,
Yeah.
first of all, the left formula has zero radius of convergence in alpha s.
This has zero radius of convergence. Absolutely, yes. So this is a that's right, an asymptotic series, which is its own challenge. Yeah.
But then my question basically is, you want to put this into some statistical
Yeah.
ensemble.
Yeah.
That is some different properties, but somehow what clashes in my head that I know from the very beginning that mathematics has no there's some logarithmic distribution which you don't control within math. So therefore, at the end of the day, what's the goal?
No. So good. At the end, so now non-perturbed is awesome. So we have to put in shape functions here. To actually get predictions of these moments, we have to convolve the perturbative calculation with a non-perturbative shape function. Like it's the other direction. Like this actually forces you to really declare your understanding of the distribution and put in all the ingredients. And so this is just this goofy approximation. But actually, if you're really going to do it, you want to do the full perturbative plus non-perturbative calculation. And indeed, that's what's done here. So here, what we're doing is we're taking existing calculations for the thrust distribution. I forget whether for this, how we treated the non-perturbative physics. Here, we might have just done a frozen coupling approximation. I forget from our paper what we did. But this is now computing of various moments. Logarithm moments, ordinary moments, mixed moments. And this is what the this constrained optimization requires you to do. It requires you to specify these numbers. Note that these numbers have uncertainties on them because these uncertainties come from scale variation, uncertainties in non-perturbative modeling, things like that. So to use this framework, you really do have to know about the full structure of the calculation. So it doesn't absolve you from doing the hard work. It's just saying that I can take that information and summarize it into a small number of numbers as opposed to doing the full distribution. And yet, you can use it to reweight the full distribution. So even though here I have order 20 numbers, and it's not the full distribution, I can nevertheless use these moments, and these moments are a good summary of the full calculation. And what you can see is as you add more and more information, you can see these error bands. It's hard to say because they're so small. These error bands are now collapsing down, where the more information you have, the smaller the error bands become. And so as you add more information, kind of in an information theoretic sense, as you add more information, you get a better constraint on the distribution, and you're less sensitive to the choice of that prior. And what's also very satisfying to me about this framework is that it also, because it's full phase space, here I computed moments in one observable and then I plotted that same observable. And of course I can do that to super high accuracy if I wanted to. But also I can look at the implications for these moments on other observables. So for the experts, broadening is an observable that has a similar structure to thrust. And as I compute more and more thrust moments, this error band that's shown in blue shrinks down to orange. So for observables that are sensitive to diject kinematics, just knowing the moments of thrust actually allow me to constrain the distribution for a complementary observable like broadening. But then there's another observable, aplanary, which is very different from thrust. And satisfyingly, adding these moment constraints actually does not give you the giant shrinkage of the error bars. The error bars shrink a little bit. But that's a good sign because you haven't actually done a physics calculation that's sensitive to that region of phase space. And so the uncertainties should stay large. And so this is an example of the way that we might imagine this being used in practice. So our paper came out in PRL earlier this year in 2025. And of course, there's a ton of different things you'd have to think about if you want to take this framework into account. Like for thrust specifically, various things, this issue of the shape function, that has to do with non-perturbative physics, as was mentioned before. But in general, you need to think about what's your best guess, what's your choice of prior, what's your hallucinating AI chatbot. If you want to put constraints, do those constraints have uncertainties? Non-perturbative corrections, the convergence of this expansion. And what I'm showing as my last thing is, what if you want to do this in a really high-dimensional, multi-differential way? What if you really wanted to use this for deployment such that an experimentalist could actually deploy this on on scale? What would you have to do in principle? And this is kind of fresh off my email from my collaborator, Ben Assi. So what we're doing is we're imagining picking a basis for all possible things that could happen at a collider. The particular basis is based on some work that I did previously called energy flow polynomials. For people who know about this is a complete basis of infrared and collinear safe observables, and you can compute moments of those as much as you want. And what you're seeing here is you're seeing, before doing our procedure, the red, green, and blue correspond to kind of your hallucinating AIs. And then as you add constraints, the more and more constraints, you see them kind of collapsing down to the correct answer. In this case, I defined the correct answer based on some synthetic parton shower. In real life, you'd want to base this on a QCD calculation. But this is now just showing one dimension and this collapse. But you really want to do this in high dimensions. And visualizing a very high dimensional phase space is very hard. With these energy flow polynomials, let's say we have, 50 to 100 of them. So here's our best guess right now about how you might visualize all of them. So this is a 50-dimensional phase space. Each bin here corresponds to a different 1D projection. And then this measure here, called the triangular divergence, is a different measure of similarity between distributions that you might want to use. And this particular one, you can see, as I add more and more information, the similarity gets smaller and smaller and smaller. And each one of these lines here, again, corresponds to an interesting way of processing collider data, which for another talk I could tell you about, you can represent in terms of graphs. And then just as something fun, there's the American movie Good Will Hunting. So the GWH here is Good Will Hunting, and there's a scene in Good Will Hunting where Matt Damon, no, is that Matt? Yeah, Matt Damon is drawing graphs, and these are known as the Goodwill Hunting graphs. Each one of those graphs corresponds to a different collider observable, and so over here you can see the convergence of the Goodwill Hunting graphs if you do this moment expansion, and it does a pretty good job. But high-dimensional phase space is really hard for us to visualize, and yet this approach, if you trust this projection, is able to take a lot of moment information together and get constraints that cover the whole of phase space. And now it just becomes a challenge of actually implementing this procedure, of actually imposing these constraints, both the theoretical calculations to get this plus theoretical uncertainties, and then the machine learning optimization to deal with the fact that the loss landscape could be quite challenging to find actually the Lagrange multipliers that correspond to the moment constraints. So the ending here is saying, different summary statistics capture different physical effects, and this is an opportunity for us to choose summary statistics that correspond to our physics knowledge. And logarithmic moments, which again, we could have computed decades ago, but no one thought to for some reason. But this approach says that logarithmic moments, they're offering important insights into QCD resummation. They have a different structure. It doesn't absolve you from having to do the hard calculations, but it gives you new insights on the types of calculations that you might want to do. OK, so this is what I wanted to tell you about QCD theory and information theory. Happy to take more questions now, and I'm on sabbatical between now and the end of July 2026. I look forward to interacting with you. And just to reiterate, if you think that you have a physics problem that might benefit from this optimization framing, I'd love to have a conversation, and looking forward to more of those conversations here at my time at IPhT. Thanks very much.
Yes, no? Ah, yes, okay. Who was? I saw a hand. Oh.
So in the first part, you describe you are using some optimization problem. So could we say that this by itself doesn't really require machine learning? No, you could assume you could use some old style minimization software, which is just deterministic. So you mean machine learning gives you a more efficient algorithm to look for the optimization?
Good. So indeed, you could ask, what does this actually have to do with machine learning at all, in the sense that I've actually collapsed what I've done onto learning just the values of Lagrange multipliers, which are just numbers. And I could use standard Minwi style optimization to, for example, find those. And indeed, that is a perfectly fair characterization of what I've shown you thus far. And it just happens to be that machine learning style optimization with neural networks, that those toolkits are relevant for this problem. But I would say that this is actually just true more generally, that a lot of people get like think about machine learning as somehow it's like this magical thing. And there are magical elements of it, and there's strategies of machine learning optimization that turn out to be extremely powerful. But at the end of the day, it's really just optimization now over a very high dimensional space, and that's what machine learning can do effectively. Now, with what I showed you here, you can actually combine this with more neural network style machine learning if you wanted to. And so that is also something that we've been exploring. But for here right now, it's just optimization. Machine learning is good for optimization, and just take advantage of the tools that people have built. And for me, actually, a bunch of what I've been working on has been in that direction. So for example, my student Sean Benavides, he gave a seminar here at IPhT a month or so ago, and what he was doing was showing you that basically you can take a bunch of machine learning problems and turn them into linear regression. You're still using machine learning, but you're actually isolating kind of a linear part of it, and then you can do standard uncertainty quantification and error propagation based on that linear model. And I feel like that's a little bit where we're kind of stepping more towards, is things that we have rigorous guarantees on, but we're still taking advantage of the machine learning toolkit. Yeah.
Jesse. Thanks. A two-folded question.
Yeah.
The first one, should I retire? The second one is, I'll try to make, so the should I retire, I'll make that a bit more precise.
Yeah.
Is there a value in improving Q in your Q of X in your expression?
Yeah.
And the second one is, what guarantee do you have that if you constrain things by, say, 10 observables, if you pick an 11th one, you have a guarantee of accuracy? And in a way, to put that more solidly, imagine you tune thrust, broadening, aplanarity, and everything. And I'll tell you what's the accuracy if now you ask your code to give me something where you put a cut on tau 2 and subjectiveness and ask for the ratio tau 3 over tau 2. Again, just to make that a more concrete example. Is there any guarantee at that level, theoretical guarantee in that case?
Good.
So numerical uncertainty bands.
So the first answer to your question, should you retire? And the answer is definitely not. Okay. So here in this telling of the story, I was painting parton showers in the same language as hallucinating chatbots, which is extremely unfair, because actually parton showers themselves are a certain regime of QCD that you're doing a calculation for. What I'm saying is that you can actually take your parton shower predictions, predict the moments using your parton shower, and tack it on to another tool. That is, you can think about the parton shower itself as a calculational strategy. So that's one thing to say. Please don't retire. Please give me your resummed predictions for as much of the phase space as you possibly can, but you don't have to be responsible necessarily for the interface with the rest of the experimental pipeline. Or you could do things that have, for example, you can consider variations in, like you could say, I'm gonna tune my shower just to predict these observables, separately tune my shower for these things, and then this approach will allow you to synthesize them without having to have the same software program have to do that interpolation. So
the question is, where is the gain then? That means that your algorithm to figure out the multidimensional perspective is going to have an easier time, you're going to need less data, or is it something which is just a more formal improvement?
So the benefit here is that if you think that actually there's a tension in the way that you're doing the calculation such that modeling one region of phase space is in tension with modeling the other region, then you just treat them as two separate modeling things, and then the information theory will interpolate. So that's one thing to say. Then the next thing that you're asking about, what type of guarantee, next thing you asked about, is there benefit to improving Q? And the answer is absolutely, because you're starting off with this prior. If the prior is stupid, then you have to do a lot more work to make it look right. So for example, in here, we're taking these curves corresponding to like changing alpha s by 20%. That means that you have to do a lot of work, a lot of moments in order to constrain things down. And so the better that your Q is, the better the procedure will be. And then the other thing is, what guarantees do you have? And so here's what I can guarantee you that will work, is that if you have an ensemble of priors and you have some confidence that that ensemble brackets your answer, then you can plot anything you want. You can see what the ensemble spread is, and then this procedure will always decrease that. That's what you get guaranteed. But you do need to have an ensemble of priors if you want to have a sense of uncertainty. So you need uncertainties on the moments and uncertainties on the priors, and then those things combine to give you the final uncertainty on the predicted results. And it's so yes, you want to improve. Yes, you want to improve the shower, or the prior of the Q. Yes, you want to get a range of priors that you think bracket your uncertainties. You can use parton showers either as the prior or as a calculational strategy in and of itself, and none of this absolves you from the hard task of actually doing the theory work. It just means that the synthesis can be offloaded to the machine, even though the underlying calculations you still need to do. Yeah.
So kind of a general question. These days there are a lot of papers coming in all different fields of sciences. Mm-hmm. And everyone is claiming to use the machine learning to solve some problems. So is there any way to judge which problems that are helpful and important, and some stuff which is irrelevant, and people just using the MI just for the word? It's like a trend. So where's the line in between? If you
Good. So this is this is another example of where domain knowledge is essential, and unless you know something about your domain and know what the problems you're trying to solve are, it's hard to know whether a machine learning innovation is beneficial or not. So I'm not going to speak for other people. I'm just going to speak for myself. So speaking for myself, the part of this talk which is most important to me personally was the thing that I did not know until I did this study, which is that logarithmic moments can be computed, and here's what they look like, and they look non-analytic. That, for me, the insight that I gained by translating my problem into a machine learning language and seeing what it required of me, this, for me, is the insight. And in fact, another perfectly reasonable approach to this talk is to say, wait, you just highlighted the value of logarithmic moments. Just tell the experimentalists that that's what they should compute. And then just compare directly your theory calculation for the log moments. Don't do any of this machine learning stuff. Just say, theorist predicts log moments, experimentalists should measure this now. And that's another framing. And so for me, the machine learning is most beneficial in cases where I learn something about the structure of my problem. And this is my own take on things. Other people have different opinions about it. But other work that I've done has had that flavor to it, where I look at something through a machine learning lens, and then I try to say, well, wait, if I didn't know about machine learning, what thing would I learn about my own field that didn't need the computer? So I mentioned before optimal transport as a branch of machine learning that's been really influential for me. But it's not the optimal transport itself, which is itself a beautiful area of mathematics, but it's the fact that I've now learned something about the structure of my physics problems from that. And in particular, I learned something about the structure of non-perturbative physics that I didn't know before from doing that optimal transport work. And now it's something that I can't unsee. I can't unsee that framing. And so for me, the machine learning, I view it as a vehicle to understanding. Of course, at the end of the day, you actually do the implementation. But that for me is the kind of the hallmark of what makes me excited. But other people have different standards. And I think this is an emerging question about this intersection of AI and physics, and a continuing dialogue about what things really will stand the kind of the test of time in the scientific domains.
Okay, well, thank you very much. We had a lot of questions, yes. So thank you again.
And thank you.